Okay, so continuing this example, we sort of came to the conclusion that because this function, it's square, right? So we're analyzing the square. It is a real function, so the absolute square is the square, and it is bounded by +1 in the range between 0 and 2 pi, since we are squaring the sine function, and sine function can be more than 1, right? So whatever it is, it will probably have two lobes of some sort, right? So with 0 at pi, right? It's still gonna be in that rectangle that it's like could be plotted in red like this, and therefore its integral is less than the integral of absolute square dx from minus infinity to plus infinity. It's less than infinity, right? So it's some constant value which we can use, calculate if you're interested, and then normalize function by dividing with the square root of c, right? So that will be a normalized function. All right, so next example, we have a function which is sine square, right? And it is sine square in the entire range from minus infinity to plus infinity. So what's the picture here? So we have we saw the sine square in the 0 to pi range, right? 0 to pi. It was something like this, and then now it's in the entire range, right? So something like this. So it's a real function, and it's a function which is positive. Well, to start, we actually squaring the sine, right? So it's a sine 4x, right? So this is what absolute square of sine x is, sine to the 4x. Again, function is real, so that's why we don't need absolute, right? So we can just square the sine square, it's sine to the 4th, and we need to integrate that from minus infinity to plus infinity in order to see if this function is normalizable. Of course, we could try to see if this function is okay based on the other criteria like continuity, like single valuedness. What else was there? Differentiability. So all these criteria would be okay because sine is a continuous function. It's a single valued. And so everything is fine. That's why we sort of only need to worry about normalizability. So any opinions on whether this integral is finite or infinite? Again, if something prevents you to answer the original question, please, pretty please, let me know what information would you need to solve the question. I'll be happily providing it. All right. Then if this doesn't work, let me know. Do you want me to just cover these examples without asking you anything? Because I thought tutorial is sort of opportunity for you to sort of interact with me, ask the questions. But if you feel not very comfortable with that mode, I could just do another lecture solving the problems. Here, some answer would be appreciated. Otherwise, I'm sort of confused what to do. We could, of course, sit for another 50 minutes. Yeah. Yeah, question is whether the function is normalizable or not. That's the last criterion, right? And the function is sine square. We are talking about example B, this one. And yeah, absolute square is a sine to the fourth. Sorry, I cannot hear you. The integral is infinite. It's not finite. That's your answer. Could you elaborate why? So that others seem to be, yeah, puzzled with that. Yeah. Right. Okay. That's a sort of legitimate logic. Uh, but on top of the fact that it cannot be boxified, it also has only positive contributions, right? So every lobe here and here, it's positive. So, and there is an infinite number of those, it's periodic. So then you sum infinite finite contributions and then you get infinity. That's the kind of the definition of infinity. So yeah, let me know what is not maybe clear here. The should be kind of straightforward that the function is not normalizable because this is infinite. All right, so with that, let's go to the example 3 or C, this one. And again, could anybody comment on continuity, differentiability, and single valuedness? Is it a single value function? And I hope everybody seen parabola at least once in their life, right? So this is parabola, plus infinity, minus infinity. Is it continuous? Differentiable? So what is potentially wrong with this function? Or maybe it's a completely physical function to work with. If our solution of Schrödinger equation will be parabola, can it represent physical system? We need the third criterion, which is normalizability. And again, we are looking for finiteness of the integral of psi squared dx. And in this case, what will be psi absolute square? What should I put inside? Well, x to the 4. And I guess this integral you could do analytically, right? So it's x to the fifth divided by 5 plus infinity minus infinity. So it's infinity, right? So that's should be straightforward. So again, this function cannot be normalized. Now we can move on to the next example, which is again satisfying all the continuity properties, right? So exponential function, how does it look? So when we increase x, it goes exponentially down. If you go into the negative, it's gonna be growing. Now, this is the function itself. So what's gonna happen when we plot the size square? Well, size square, what is size square here? It's e to the x squared. Oops. So that is e to the minus 2x, right? So the function will just be steeper, pretty much the same, right? And if we again look at the integral or area under the plot, we'll get infinite value, right? Because it is in infinite area, since we are taking integral from minus infinity to plus infinity. And in all negative x, we have over 1. Value of 1 is for x equals 0, and for everything else, you get more than 1. Okay, as you can see, there's a pattern here. So both c and d and b and d, all these functions, they are not okay because we get the integral of size squared, which is infinite, right? So we cannot normalize these functions. These functions cannot be representing physical system because their absolute square cannot be probability density, right? So that's the sort of conclusion we can make about BCD. Function A was fine. And now we are left only with a function which is also known as Gaussian, right? Now, who wants to tell us about Gaussian? What's the thinking process here? We would follow the same pattern as BCD, or you think it will be more like A? So first, this Gaussian function looks like this. And the absolute square will look even, again, since it's real, like this. So even steeper drop. That's absolute square. And so what do you guys think? Do we have a integral minus infinity to plus infinity for this function minus 2x squared dx more than infinite or less than infinite? Yeah, it is finite. Can you prove that? Okay, so it is true that it's finite, and there's a formula for the any integral of the function like this, right? And it is a square root of pi divided by alpha, if I remember correctly. Maybe there are some constant factors I'm missing, but in principle, it's not that hard to derive this formula in a sort of hand-wavy way. And it's actually on Wikipedia as well page, but it turns out that this Gaussian integral, like this hand-wavy way that can be at the physical level of rigor used to arrive to the formula, actually is quite simple and it's nice. All you need is to say, all right, I don't want to deal with a single integral. I want to do double integral for x and y. And it turns out that when you go from 1 dimensions to 2 dimensions, things become simpler because you can use polar coordinate system. What this is effectively you say, all right, I will take this integral and we'll multiply it by its copy, like this, right? So one integral has x as a variable, another integral has y as a variable, but they are all integrated, so it doesn't really matter. X and y are more or less the same. It's just a coordinate, right? So this is the square of the original integral, right? Because the fact that one is integrating with respect to x, another integrating with respect to y, doesn't matter. They're running through the same ranges. So it's a I squared. But then, because x and y are independent, what you can do is form it as a double integral, dx dy, and use nice property of exponent, right? Like this. Oops. X squared, y squared. And that's where we sort of, those who are familiar with the multivariable calculus, they know that there is a way to, well, you could study things in the xy coordinate system or polar coordinate system, and we'll use that polar coordinate system later more, especially when we come to like a hydrogen atom or particle on a sphere problem. But the idea is that you could essentially, integration is a summation, right? So you could sum in the different ways. And the nice thing about summation, you could sum essentially in any order you want. That's where things get a little bit mathematical with that statement. Things get a little bit mathematically challenging on a higher level of rigor. That's why mathematicians usually have theorems about these Gaussian integrals. And I'm not using any theorem. I'm just using sort of lower level of rigor that works here, but may not work on some pathological functions. So, but here things work, and the way they work is I'm substituting essentially xy by r and phi. R and phi is a coordinate system where instead of x and y, I have radius vector and the angle, right? So you can cover space with tiles of the squares of x and y, right? Or I can cover the space with just different radius vectors and different phi's. Phi goes between 0 and 2 pi, radius goes between 0 and infinity. And the integration is here, instead of dx dy, you get r dr and d phi. So this is between 0 and 2 pi. And this one is between 0 and infinity. And then the integrand here is, well, it turns out we already seen this formula that r is square root of x squared plus y squared. So nicely, we have x squared plus y squared in the exponent, right? And so therefore, you get, instead of this exponent, you get exponent of minus alpha times r squared, right? Because it's x squared plus y squared. I can substitute it by alpha minus alpha r squared. And so because of that, the integration becomes very easy. So this integral is just giving me 2 pi, right? Because there is no phi dependence. This thing doesn't depend on phi. So this integral just gives us 2 pi. And this integral, the r dr with this exponential function, is very easy to do, because simply it's a r e to the alpha r squared dr, 0 to infinity. And that is, okay, we just do the substitution of the variable. It is minus alpha r squared. And here we have d of alpha r squared. We've divided by alpha and divided by, I guess, 2. All right. And so then I simply get, what do I get? From 0 to infinity, I get 1 over 2 alpha as a value, because it's a essentially integration of minus exponential of minus x, max x, right? So where x is alpha r squared, right? So this is easy to get, 1 over 2 alpha. And with 2 pi here, we just need to take a square root of 2 pi divided by 2 alpha, right? Because this is product with this, and the square root because we were calculating square of original integral, right? So that leads us to the final expression pi over alpha. That's a Gaussian integral, right? So if you are, this is also shows the power of polar coordinates sometimes, and power of the fact that okay, sometimes the square of the quantity you're looking for is easier than the quantity you're looking for, surprisingly. Okay, so, but long story short, the integral is finite, and so we can conclude that this is a legitimate wave function, and the answers to the questions that were asked is yes, no, 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 yes. Okay. Any questions? You have plenty of time practicing it at home, but if you have any questions now, I'll be happy to answer. All right, if there are no questions, let's move on. So when we normalize, don't forget that we need to square the function right there, f of x, to get the constant. That is, well, requiring f of x be an absolute square. And then because of that, you use 1 over square root of c. And here's some examples, some exercises where possible, find the normalization factor for the following wave functions, right? So example A, how would we do it? So as the prescription tells us, we form psi of x squared, which is 1 minus x squared, right? It's a real function. And we take the integral, not in the entire space, but from -1 to +1, because the function is defined this way. So if the function is defined only in a specific range, you could safely assume that the function is 0 everywhere else. Okay, so that's just a short way of writing this. Okay, or the entire space is for a particle limited from -1 to +1. Or if you're not sure, you always ask. Okay, so if it's exam, even homework, and you're not sure, send me email or ask me at the exam. Sometimes it happens. Some condition could be missing, but no one will take points from you for asking. Okay, so in this case, it's just the space is -1 to 1, and we integrate in 1 minus x squared dx. Okay, and so that should give us constant that we will then turn into 1 over square root of c, a factor, right? So the rest is just a simple math. You need to square it. It's 1 minus 2x squared plus x to the 4th dx integral. Okay, anybody did it already? Okay, so what's the answer? Let's see, square root of 15. I guess this is already, yeah, normalization. Okay, so this is c. And from that, 1 over square root of c is square root of 15 divided by 4. So that means the c should be 16 divided by 15. Is that what you got? Okay. And everybody else, should I do the integration, or you are fine with this procedure? So from here, -1 to +1, the c should be 16 over 15. And that's how you get to the answer that was listed. So this is the moment where you could ask how this is done. If I don't see your hand, I will move on. Okay, let's be clear. So if something is not clear, please ask. But this type of problems that you're gonna get in the next homework, I think in the current homework, it's just testing your calculus abilities and the probability density interpretation understanding. So it's already up there. So for 1 week, as I promised, next Monday, there will be another homework that will cover this topic, normalization of functions. And that's where you're going to be doing this in a few examples. Okay. And I guess this is just really pure math. You want just to do this carefully and accurately without making mistakes, right? And these are the solutions at the bottom. You could check yourself, and hopefully that's clear how to do it, right? So we could move on to the next topic. All right, so the next topic, we will talk about operators and why they are important. Turns out, just to give you a big picture first, in any physical theory, any physical theory only useful if it can predict things we observe in experiment. And in quantum mechanics, turns out any property you want to measure, right? So if you take your system, your particle, in some container, right? So you encapsulate the particle, you have some probability density, and it integrates to 1 in your container, right? So that's how you know your particle is in the container. It is represented with some wave function. You take it to the lab. By the wave function, it could be a molecule, right? So molecule has a wave function. So you take your molecule to the lab, you measure some property, and the interesting thing about quantum mechanics is that any property you could think of that is measurable always correspond to operators. Okay, so these objects that take functions, that eat functions for the breakfast, lunch, and dinner, right? So they take functions and produce other functions, operators, and that's why they are important. They connect mathematical world of functions to things we observe. But that connection is a bit tricky, okay? So that's why we study them. But once you learn about that connection, once you learn how it all is connected, then it becomes super easy. If you want to predict something, all you need to remember is what is the operator corresponding to the observable that I am interested in. Here are some examples. Let's say if you're interested in position, 1 dimension, 3 dimensions, our world is 3-dimensional, right? So we live in 3-dimensional space. So operators principle will be for 3 dimensions, but the basic principles is easy to illustrate in, of course, 1 dimension, right? So the fewer dimensions, the smaller the, like mathematical difficulties with integrations, all that stuff, right? We shouldn't forget about 3-dimensional world, but illustrations are easier in 1D. That's why I will be doing a lot of illustrations in 1D, but keep in mind that the world is 3-dimensional. But it's just a slightly different math, okay? So conceptually, the same idea. All right, so now if you're interested in, let's say, position, so there is an operator, it's multiplying by x. If you're interested in 3D position, it's, well, has 3 components, x, y, z, multiplying by x, y, and z. That's the operator that defined by r. Now, momentum is another important property. Classical momentum is mass times velocity. And then there is a quantum expression. Does it come? Yeah, so there is a quantum expressions later. These are classical operators from classical physics. Classical, they are not even operators, they are just functions, right? So the quantum ones are coming later, right? But just to remind you, these are type of operations or observables that we will be interested in. Say kinetic energy is the next in 1D and in 3D, and then potential, energy, and many others. If you're interested in some, then there is always, quantum mechanics always has an operator for that, observable. Right, so here I have quantum version of the same observables. Okay, interesting. All right, anyway, so this is a position, momentum, this is something for you to always remember, that momentum is derivative of the position. That's the operator. You differentiate the function that the operator is acting on. And then you have, well, kinetic energy. It's just a function of momentum. You differentiate twice because it's a p squared. And if we do this p squared, then minus I gets you minus I squared is still -1, right? And then h gives you h squared. 2m is just coming from here, and that's a second derivative. That's something I've shown you last time, but here again we have that kinetic energy operator, which essentially is responsible for electron not falling onto the nucleus. It's responsible for component of energy in quantum world that will be higher if you try to squeeze the wave function to very compact place. Then the squeezing always increase kinetic energy, simply because the curvature of the function, how curved it is, will increase when you try to put the same, well, like absolute square of the function is still integrates to 1, right? So it needs to have area under the curve, and then the curve becomes kind of more spiky, and that drives kinetic energy usually. Okay, so that's the basic intuition. Then potential energy, it's just a function of x or a function of any other coordinate systems. Like we will talk about molecules eventually. In molecules, we have electrons and nuclei, so they have different coordinates, and we know that since the electrons and nuclei are differently charged, right? So then what we have is Coulomb interaction between position of electron, position of the nucleus, but those are only coordinates, right? So don't think of them as representing the particles. Particles are still represented with wave functions, at least electrons, and nuclei as well. Just they are more localized wave functions. Okay. Now, total energy is the sum of kinetic plus potential, and also the operator for the total energy is the Hamiltonian. So that's why the Hamiltonian has important role that it plays. It gives to the observable total energy the operator. Now, the tricky part between this correspondence is that properties in classical world or in the world that we observe, these are position, momentum, kinetic energy, potential, total energy. They're also numbers, right? So they're also numbers, usually. We could measure kinetic energy of moving objects in the classical world. Cars, baseballs, whatever, puck, hockey puck, right? So how quickly does it move, momentum, kinetic energy, that sort of stuff. Now, operators, on the other hand, they are really far from numbers. If you think about them, they are 2 degrees out, right? So we know that the closest to the numbers are functions, right? So they take number and produce another number. Operators, they don't do that. They take functions and produce another function. Now you could appreciate that connecting operators to numbers is a tricky business, right? Because seems like they are well separated from each other. But yet, quantum mechanics does that. It explains how to connect operators to numbers that you observe. And that's the beauty, right? Okay, so this is some simple statements like what is operator, mathematical properties. So some of the stuff that was already explained, but just to give you a few more examples. Yeah, my favorite is differentiation. It's probably something that is less trivial than just multiplying by x, right? So it actually changes, well, it changes things in some profound way, like you take x squared, it switches to 2x, right? So these functions are very different. One is linear, another is quadratic. And then multiplication by x squared, for example, right? So that is also an operator. So it takes 3x and then it gets you 3x cubed, right? So it's operator. And then there are some exercises I will probably not go too into because it's well, they're simple. I could kind of go with you on the first one. Well, okay, so the first one is trivial. It's just differentiation of x6, x to the 6, right? So apply an operator to a function. Nothing complicated here. If something is confusing, please let me know. You could essentially what's happening here is we're just using different language for what you already have seen in calculus, right? So they didn't call this as an operator. They just taught you how to differentiate. Now this is more interesting, right? So you could see that you could bunch together two operators and create a new one. And that's what we talked about, is like linear combination of operators again operator. And so how do we apply this linear combination to a function? Well, since it's linear, we apply this part and this part separately. So we get the result. Okay. And so on and so forth. We can have this, and this is more non-trivial example because it uses this three-dimensional number. Square is just a short physicist notation for d square, sum of second derivatives. Those who've taken the multivariable calculus may have seen that. Right, so for this course, it's as linear algebra could be useful, but I feel like you could, in principle, get by without taking the multivariable calculus, because we will introduce all the quantities. So now, as you could see, it's more complicated operator, but it's a sum of, and you just apply each and sum the results. You could check yourself that indeed you will get this answer. All right. And probably let's say the last thing for today, because time is running out, is just to say that there is a product of operators defined. As I promised, it's operator algebra. So you could think of operators as these abstract vectors that you can add together, multiply by constants, but also it's algebra, so you could multiply them. And what multiplication means, really the same. I think it's very relevant to life. All right, so operators is like operations that you do in your life. You wake up in the morning, go brush your teeth, take a shower, go have breakfast, put your shoes on, put your clothes on, maybe in a different sequence, and then go to the university, right? So the A and B are these operations. And when we say A multiplied by B, what this means is we apply B first and then A to the result of what B did, right? So this is what shown here. B is applied to F, and this is going to be function of some sort, g of x, let's say, and A is applied to G, right? So they're sequentially applied. That's what multiplication means. Okay. And so then there is one interesting operator, which is really it's kind of could be considered as a mathematical kind of one of those things that mathematicians like to give name for everything. Like identity is like operator that doesn't do anything; it just multiplies by one. Right? So there's no action, non-trivial action, but yet it is useful. It's needs to be separated from multiplying by 0, which kills the function. Right? But multiplying by 1 stays keeps the function the same, identity. And then nth power of operator is just applying operator n times. So that's pretty much the algebra of operators that we'll be using. And we'll get to the connection to experiment and the notion of eigenvalues and eigenfunctions next time. Okay, because it's a very important topic. I don't want to start it now, but it will be a next thing we will learn, and it will be crucial to connecting operators to numbers, which we get in experiment. Okay. With that, that's all for today. If you have any questions, I'll be happy to answer.